Let's just go very quick through it, and I'll tell you what was my idea. So on the first problem, my whole idea was to combine two problems into one, no? Two solutions. So you have the static unbalance, the one we did the other day, and you have the one we did right before that, which is the base excitation. Okay? So basically, take the solutions, both of them, and try to come up with a solution following the same procedure. Okay? So that's the whole idea. That you go through the whole process again on your own. Second one was to take the problem that we're doing the other day and just basically, try to put some more data. So consider the turbine, and this time, I put a prerequisite on how much needs to bend the post, okay? I assume a damping of 2%, even though I don't know if there's damping in this problem or not. I don't think we did it with damping. We must assume damping or not. And that the blade rotates at 60 revolution per minute. Okay? If you need some more additional data, just put it. I think I assume also to assume cast iron. Yeah. Okay, just any material. And then the last one is again to make you go through the process to find the equation of motions. This one I kind of took it from the book, these two equations, but I kind of came up with my own problem, okay? So it's like, out of these two, which system will lead to the lowest deflection at the CG? Okay? So the idea is just to make you go through the equations, and really I have no idea, okay? I will have to guess. I could give you an educated guess, but I don't know right now on top of my. Personally, I think the one, I don't think the damp is going to do much. I will look more about the stiffness, no? Mm-hmm. So what is better, to have the spring close or far away from the point you want to have the lower deflection?
I would say close.
I would say close as well. But I don't know, okay? Let's go and check, okay?
Right.
Let's see if you need to prove it. So that's it, just to make you go a little bit through the process of having to do those problems. So let's see, last time we started the chapter about the multi-degree of freedom or 2 degree of freedom. And there we go.
And sorry, Professor, what day did you say the homework was due?
I think it's the 13th.
13th, okay.
Yeah. I should be back, actually on the 13th, I should be back here, but I have actually a meeting at 8:15 in the morning in Orlando. But I think that by this time I should be able to, be done with the meeting and be back. But just want to let you know. Right. So anyway, 2 degree of freedom. So what is the meaning of 2 degree of freedom? Is that we have two rigid bodies with two different motion, x1 and x2, no? So each one will be 1 degree of freedom. So again, we follow the same steps as we have been doing for the 1 degree of freedom. We do a free body diagram. We put all the forces. We write down Newton's equation. We come up with the equation of motion. And then, since there is 2 degree of freedom, we put the equation of motion into the matrix form. Now, we follow exactly the same step. How do we find the solution of this system? For, let's say, the free undamped problem, the free vibration without damping, we assume harmonic solution, all right? So that means we substitute the x1, x2, we take the x dot, a dot, we end up with this type of system. So what is this type of system? Or this one over here. When this will be satisfied, either when this is equal to 0, which is a trivial solution, correct? Mm-hmm. Or when all this term over here will be equal to 0, okay? So what we need to do now is to find for the determinant of this. I want the determinant of this. We then need to determine what would be the values of x1 and x2 that will make this 0, no? All right? So last time I think we just stopped at finding, if you find the determinant of this is equivalent to come up with the characteristic equation that takes this form. The characteristic equation yields to what? To two to two roots of this quadratic equation. So this one is to gamma to the fourth, or lambda to the fourth. So if we take the quadratic equation of this, the variable will be lambda squared, no? Yeah? And at the end, I think you end up saying that what's very important over here is to realize that each one of those lambdas are actually equal to what? To the natural frequency. So what is the meaning of the natural frequency? So, yeah. So the natural frequency for this problem, for example, will be what? At one frequency, it will vibrate one with respect to the other, and at the other frequency they will meet. And at one frequency it will vibrate at the same time, on the other frequency they will go in opposite directions. Alright? So what's important to identify is that for each value of lambda, over here, lambda 1 or lambda 2, we can solve this equation. You see here you have lambda. So for each value of lambda, we're going to have different solutions for lambda for x1 and x2. And when we solve for x1 and x2, this is what is called the eigenvector. Okay? All right, so let's do that. So 75, 76, 77. Okay, the eigenvalue prime is extremely important, okay, in engineering. Okay, so if you want, let me just rewrite one equation over here. Okay, let's just say here, next, the two values for lambda 1 square and lambda 2 square are used to determine the vector there is no dot x1, x2. Okay, so for that, let's say case 1, lambda equal lambda 1, or lambda 1 squared equal lambda 1. So we use the equation. What's the equation we're going to be using? The minus m1 lambda 1 squared that we had plus k1 plus k2 here we had minus k2 minus k2 minus m2 lambda 1 squared plus k2 plus k3. Here we had x1, x2, and this should be equal to 0. Okay, so let's go back over here. So when is this going to be equal to 0? Or this equation? When ei lambda t is equal to 0, which is the trivial solution, or when all this term within brackets is going to be equal to 0. Okay? Mm-hmm. So now that is what we are solving. That's this equation over here. But before doing that, what did we need to do? We needed to solve for the values of lambda within this equation because they were unknowns. Correct? So you think about it. Here, how many unknowns do we have? We had lambda, lambda 1, lambda 2, x1 and x2, no? How many equations do we have? 2, no? One for x1, one for x2. So we didn't have enough equations. Where did we go get the additional equation? We calculated the determinant of this matrix in order to determine what will be the two values for lambda 1 and lambda 2. Okay? Now that we have lambda 1 and lambda 2, we can go back to this equation and solve for the values of x1 and x2 that will make this 0. Okay? So the first case we do is for this lambda equal to lambda 1, so we have here all this square. So when will that be equal to 0? What do you need to do for that to be equal to 0? You will do minus m1 lambda 1 square plus k1 plus k2 times what? What is the first equation? Times x1, correct?
Minus k2 x2.
Minus k2 x2 needs to be equal to 0. Or what is the other option?
Minus k2 x1.
Minus k2 x1.
And then that other term multiplied by x2.
Yeah, plus this term over here, the minus m2 lambda 1 squared plus k2 plus k3 x2 will be equal to 0. Okay, so remember what I'm trying to solve here to determine the vector x1 and x2, no? Alright, so what would be then the vector? I'm going to reverse the order a little bit, but it should not matter, you can do either one. So it should be x2 or x1, if you want, let's do x1 over x2, doesn't matter. x1 over x2. Okay? I'm going to make here something different. I'm going to add here a 1 and a 1 to show that this is for the lambda 1, okay? So if we look at the first expression, what should be x1 over x2? So x1 over x2 should be equal to
k2 over everything in the curly braces?
Yeah, k2 divided by minus m1 lambda 1 square plus k1 plus k2. Or, if we look at the second equation, it would be equal to what? So it should be x2, no, x1, so it should be now
Everything in the curly
x1,
braces over x2, or over k2, sorry.
so x1, so they will reverse the order at the end of the so we do x1 should be k2, now this is correct. This one will give you,
It should be that term in the curly braces divided by k2.
yeah, so minus m2 lambda 1 square plus k2 plus k3 divided by k2. Okay, are you done copying this? Now what do we need to do? We need to do exactly the same thing for lambda equal to lambda 2. So case 2, lambda equal to lambda 2. Let me do one thing here. What are we today, June 8th?
Yes.
Lambda 2, so I'm just going to recopy the same thing again. Minus m1, but this time will be lambda 2 squared plus k1 plus k2. Minus m2 lambda 2 squared plus k2 plus k3 minus k2 minus k2 x1 x2 equal to 0. So that's going to give us what? Minus m1 lambda 2 squared plus k1 plus k2 x1 minus k2 x2 equal to 0, and minus k2 x1 plus minus m2 lambda 2 squared plus k2 plus k3 x2 equal to 0. So this is going to give us x1 over x2, and I'll wait for you here a little bit. Okay, so what is that 2 meaning over here? Is that this is the vector x1 over x2 for the second value of lambda, no? We have the same thing for here. This is the value of x1 over x2 for the first value of lambda. So we have that this should be equal to what? K2 over minus m1 lambda 2 squared plus k1 plus k2, or minus m2 lambda 2 squared plus what is it, k2 plus k3 over k2. Okay guys, all this stuff looks ugly, and it's just gonna get more, it's just gonna get uglier, because I'm keeping everything symbolic, okay? But once you get values, this is pretty quick. Okay, now, why do we need those x1 and x2? What was the assumed solution? x1, lambda 1, no? So we found lambda 1, but do we know x1 or x2? No, we found lambda 1, lambda 2, but now we need to determine x1 and x2, no? Yeah? So we're doing all this stuff in order to try to find x1 and x2. Okay. So now this is important. Let me do it in blue, another color. The black doesn't write this much anymore. So the eigenvectors corresponding to each eigen value, lambda 1 squared and lambda 2 squared. So what is the meaning of eigen? What does eigen mean? That's not that important, but basically this in German means proper. It's like proper values or proper vectors, okay? Eigen means proper in German, but I don't like those numbers, so those that semantics. So if you want, what I'd rather you to remember is that we already say eigenvectors for you should be what? Sorry, eigenvalues should be what?
The natural frequencies?
Natural frequencies. And the eigenvectors I want you to remember them as something called mode shapes. So what do you think is the meaning of mode shape? Exactly what I mean is, what is the shape of the deformation of the object? Okay? All right. So what is the first eigenvector? So first mode shape, or eigenvector, but I'm going to call it mode shape, corresponding to lambda equal to lambda 1, we're going to call it x bar 1 is really equal to what? x1, 1, x2, 1. Yeah?
Mm-hmm.
So the bad thing is that, okay, we can leave it that way if you want. And then x2 for the second mode shape would be equal to what? x1, 2, x2, 2. Okay, let me do here parenthesis. This is related to vibrations, okay? But I'm going to move away from the problem of the two springs. I'm trying to explain what is the eigenvectors or the eigenshape, all right? I think it's easier if we look. If you have a simply supported plate, okay? And let's say I take it, I move it, and I'm going to make it vibrate. So how is this going to vibrate? This can vibrate this way up and down, no? Yeah? So the frequency at this which will vibrate, we can say will be omega 1 squared will be equal to the first eigenvalue. Alright? This will correspond to this frequency. This will be the frequency at which it will vibrate. What would be the mode shape? This line over here, no? Is the shape of the deformation. Now, the same beam and everything. Let's say you are able to increase the frequency. So how will this vibrate? I mean, let's see if I can do this a little bit differently. If I take this piece of paper, I'm probably not going to be able to do it with a piece of paper, but if I take this piece of paper and I push at the end, what's going to be the deformation? This shape, no? Mm-hmm. But if I was pushing harder, you can kind of see that you can get the sound wave.
Yeah.
Okay? It's easy to see with a ruler. So basically what I'm trying to say is that if you have one frequency, this is going to vibrate on this shape. If you increase the frequency, this is going to start vibrating under this form, no? Okay? So, when it's this shape, when it's under this form, will the frequency be the same or will it be a different frequency?
Should be different.
Should be the seventh frequency. Okay? And now, what would be this? This would be a different mode shape. Okay? So, for each frequency, there is a specific eigenvector or mode shape. Alright? So you want, the mode shape is attached to the frequency. Okay?
So should we expect the eigenvectors to be values or functions?
No, eigenvalues, they are called values.
No, the eigenvector.
The eigenvectors will be vectors.
Okay.
I mean, they should be vectors. Okay? But something here which is, it's hard to understand, but I'm going to say it now, and maybe, you will kind of understand it. The eigenvectors will give you the shape of the deformation, but they will not give you the values of the magnitude. So basically what an eigenvector is giving you, a mode shape, is giving you the shape of the deformation, but it's not giving you the exact value of the deformation.
Okay.
I know that is confusing enough. It's like, what is an eigenvector? It's like pointing to the direction. It's giving you the direction of the vector if you want, but it's not giving you the magnitude of that vector.
Okay.
The magnitude of that vector depends on, I mean, I didn't put it, but if you think about it, there's an infinite number of solutions. Yeah, you want to look at the eigenvector. Imagine you have one vector at a certain frequency that is given by this. There's an infinite number of eigenvectors that will give you the direction of this vector, no? But there is not a single one that will give you what is the length of this vector. So the eigenvectors only give you the direction, but not the magnitude of the deformation.
Okay.
Right. So we see here, we are here. Okay. So this will be page 89, I guess 80. I don't know why the impression that I wrote 80 already like 3 times on different pages. But. Okay. So now I'm going to try to simplify a little bit the notation. So let's see. Now the notation gets heavy, but once you put values, it's not really complicated. So recalling. The assumed solutions. So what were the assumed solutions? The general was x of t will be equal to x e I, what did I use, capital omega or, no, lambda. So x of t equal capital X e I lambda t. So, the responses x1 t and x2t are what? So here's when you need to be careful. We have x1 of t. Okay, I'll change the notation a bit here. x1 of t will be equal to what?
The first eigenvector, ei lambda 1t.
So it will be the one x1 so basically it will be, yeah, so we'll have x1 of 1, then what do you have here? x2 of 1, Yeah?
Mm-hmm.
EI
It should be lambda 1.
lambda 1. Yeah. Lambda 1 of t. Okay? And x2 will be equal to the same thing here, but x1 of 2, x2 of 2, EI lambda 2 of t. Okay? So now this is going to become complicated. So what is the final solution then, x of t? Because this is the response for what?
For the first natural frequency?
For the first natural frequency or the first or for the first mode shape, no?
Mm-hmm.
So the total response if we assume this would be what? X of t should be equal to what?
Would it be a matrix of the two?
Would be x1 of t plus x2 of t. Remember we did the same thing, no? For 1 degree of freedom. But then what will happen?
Mm-hmm.
You will have over here what? What are C1 and C2?
Constants of some kind?
Yep, are constants to be determined using what?
Initial conditions.
Yep. Okay, so at the end, we want to be, and that would be the last thing I write. I have a lot more on the class notes, but will be. So what could be the general form of the equation? We could have x of t will be equal to what? C1 x1 of 1 x2 of 1 ei lambda 1t plus C2 x1 of 2 x2 of 2 e I lambda 2t. So that doesn't look too pretty, no? But I mean, you see that basically it's exactly the same process as for 1 degree of freedom, but we did 2, and it started to get more complicated. So, all right, maybe I should go and take again those pages. Trying to give an explanation because this is very important for some applications. So what would be, this is C1, this corresponds to mode 1, correct?
Mm-hmm.
This corresponds to mode 2. And if you want to look at C1 and C2, C1 and C2 could be considered as some weighting values that will tell you how much of the response is given by this first mode, okay? How much of the response is given by this one, all right? So, that doesn't happen a lot in And it will happen in vibration if you want. So what would happen, for example, what do you think should be the result if we have the same beam that we had before, this one over here? So I'm going to make the easy case. And let's say that initially, instead of being the free vibration, we have a force applied over here. So how is this going to deform?
It'll start to bow up, probably.
It will bow up, and if it's right in the middle, no?
Mm-hmm.
The solution of this line over here should be basically given by what? C1, X1, X2, 1, 1, EI omega 1t, no? Plus whatever, the C2. So if the force is in the middle, what should be the contribution from this mode?
0.
0, okay? So 0 will probably be, C2 will probably be 0, okay? But now what happens, so I'm going to do a case, a completely different case. What will happen now, let's say we put the force, so if you look at it, here is the maximum deformation, no? And the maximum deformation corresponds with this one, 0. Okay? It's in the middle. But what happens now if we decide, let's say, to put a force just over here, okay? Instead of putting one up and one down, we just put one over here. So what would be the shape of deformation of this? So I would guess it can probably look something, let's say, like this, no?
Maybe.
Yeah? Maybe. So now, the total response of this curve over here will have part of this curve, agree?
Mm-hmm.
So we'll have some type of value for C1. But this time, will the participation of C2 be 0?
No.
No. The C2 line will have to get a better result, no? So this time the C2 will be different than 0. Does that kind of make sense? So if you think about it, if the load is right in the middle, one mode should give you the exact answer. Now, do you think two modes should give you the right answer if the load was over there? Probably not, but it's probably going to give you about 90% of the exact value. So the more exact that you want the solution, what do you need to do? The more modes you need to consider. Mm-hmm. Okay? The more modes of vibrations. And that is what is behind everything which is in controls or final element model analysis is all about that. So for example, why is that important? Let's say for controls. Under how many modes can a structure vibrate? A car can have thousands of modes of vibration, no? Can you control all the modes of vibrations?
Probably not.
Probably not. So which one are you trying to control?
The most major one?
The major one, okay? So what is the way to determine the major one numerically? They do those numerical simulations and they do a final element model and they run what is called the eigenvalue eigenvector problem, okay? And once they start looking at the solution of the eigenvector eigenvalue problem, they can see, they can do an analysis to know which one of the modes will be the more dominant. So if the load is in the middle on the first one, we can see that the first one will be dominant. Now, if we put the load right over there, like say 1/4, is it obvious now that the first mode will be dominant? No, probably I will look like first mode will probably be about 40%, second mode will be probably about 60, no? Yeah? So would you be able to control the system by just trying to control one mode? I don't know. Okay? All right? But this is extremely important, the idea of eigenvalues, eigenvectors. So one structure can have an infinite number of eigenvalues. To each eigenvalues corresponds a certain mode shape. Okay? Mode of deformation. So you need to know what is that mode of deformation. All right, so let's do one example. I'm not going to use beams. We can do that later on if you want, but it's not really part of this class, but we can do it. So let's do one example. With values is a lot faster, okay? And it's And MATLAB will solve it for you very quick, but solving the problem is not the important part, is to understanding the solution. So in this problem I have, so exercise, for example, I think it's one example, so we're going to do it together. All right, so we're going to have one block of mass M1. I'm trying to do the simplest case. Connected to a block of mass M2, and both of them are connected by a spring K. All right? So we follow the same. This will have a degree of freedom x1. This one will have a degree of freedom x2. So let us take some data. M1 equal to 1 kilogram. M2 equal to 2 kilograms. I'm trying to make it easy. K equals to 200 Newton meters. Okay, so over here, which is what I don't want you to do, okay? Where is that page that I have? Okay, what could you do? You could come to this problem, no? Look at all the equations that we derive and say what? K1 and K3 will be equal to 0. C1, C2, C3 will be equal to 0, no?
Mm-hmm.
Substitute into all those equations and find the solution. But, you know, I'll show you the general process, but let's try to go through the process together. So one, what is the first thing we need to do?
Free body diagrams.
Free body diagram, perfect. Okay, so what will be your free body diagram?
M1 would have a spring force going. You could draw it either left or right. Left is probably easier.
Yeah, it doesn't matter which way you do it. So this will be here, one will be going this way, then this one will be going
the opposite.
on the other direction. And the value here should be equal to what?
Kx1 on the left, or no,
Okay.
X2 minus X1?
Yeah, it doesn't matter, x2 minus x1, okay? The math will give you the same at the end. It shouldn't matter. And now, we use Newton's law to write down the equation of motion, which will be what?
It would be, for M1, it would be...
So for M1, would be what?
Kx2 minus X1
Kx2 minus x1
is equal to M1 X1 double dot.
Yeah. So basically you're gonna have that M1 x double dot 1 plus
Kx1
Kx1
minus Kx2.
minus Kx2. 0. Same thing for this one, we'll have what this time? Minus K x2 minus x1 equal to M2 x double dot 2. So we have M2 x double dot 2 plus
Kx2 minus Kx1.
plus Kx2 x2, no?
Mm-hmm.
Minus K1 minus Kx1. Okay, or if we put that in matrix form, what should we get? Okay? Plus what?
Just k times the vector x1, x2.
And without even looking, I should say this should be, yeah, this should be k1 plus k2, so it should be k, no? Going wrong, so it should be k.
Oh, and then minus k.
Minus k.
And then minus k, k.
Minus k, k. x1, x2 equal to 0. So I'm going to try to go symbolic for as long as I can, but as soon as we solve for the eigenvalue, I'm going to put values, okay?
Alright.
So now, what do we need to do with that equation?
Assume a harmonic solution.
We need to find the solution, so we assume harmonic solution. So x would be to capital, no, would be, what did we assume before? Capital, yeah, did I do this, capital X, one before, no, yeah? E I lambda t. What do we do with that equation? We differentiate it once, no? Twice. Let me just do it once if you want. What will you get over here? I lambda x e I lambda t, no? Or you will get the double dot equal to minus lambda square x e I lambda t, and you substitute into that equation. All right? So now I lost track of the pages completely. So, we finish this block. This is the second block we finish here. So, 83. So now if I substitute, what is the shape of the equation? E I lambda t. What should we get? Minus lambda square m plus k minus m1 minus lambda square m2 plus k minus k minus k x1 x2 equal to 0. Okay, now what do we need to do with that equation?
Find the determinant of the matrix in
Correct, but we need to find, the goal is to know when this is going to be equal to 0, no?
Yeah.
So first thing, we need to find the determinant in order to find the values of lambda. When we have the values of lambdas, we can substitute in the equation, we find the values of x1 and x2. Okay? So let's solve for the determinant of the matrix. So determinant, we start saving some time, okay? Will be equal to what? Minus lambda square m1 plus k times minus lambda square m2 plus k minus k squared equal to 0. So if I do some algebra with this, what you're going to get? M1, M2, lambda to the fourth,
could combine like terms saying minus m1 plus m2
will be
minus square
minus, so minus k m1 plus m2 lambda square, no? Minus,
plus k squared minus k squared.
did that one cancel out? Yeah, because you have this k squared minus k squared, no? Okay, so this one is easier than what I think, this problem, no? Equal to 0. So let me just do one more step, might be easier to understand. So this will be lambda squared factor of m1, m2 lambda squared minus k m1 plus m2. So as you see, you don't need to know a lot of mathematics to solve these problems. So when is the equation satisfied?
When lambda squared equals 0,
Okay.
and when the thing in the brackets equals 0.
Correct. So we can say the roots, then you could go and substitute, are what? But the result would be lambda could be equal, so lambda squared could be equal to lambda 1 squared, which will be 0, no? Okay? We'll see what is the physical meaning of this one. And what should be the other term when the term within the bracket is also is equal to 0, no? So this will give you what? Or lambda squared equal to lambda 2 squared should be equal to what?
K m1 plus m2 over m1 m2.
K m1 plus m2 divided by m1 m2. Okay, so remember what we said at the beginning is that lambda 1 squared is really equal to the first natural frequency. Okay? So now let's start putting some values because otherwise this is going to get too complicated. So, or, I'm going to start using the blue, right, it's a lot better. Lambda 1 squared equal to 0. Lambda 2 squared will be equal to what? What were the values we selected? I think k is equal to 200. 1 plus 2 divided times 1 times 2. So what is that going to give us? 300. Okay, now that we know lambda 1 and lambda 2, what do we need to do?
Plug them back in.
Plug back into this equation and solve for x1 and x2, no? Okay? So let's say for lambda equal to lambda 1 squared, the above equation becomes what?
Becomes k minus k minus k and k in the square brackets.
Yeah, so you want to start putting values, so it will be, maybe we can do it without the values. Let's try to do it without the values, so symbolic. So minus lambda 1 squared m plus k, so same as before, minus k minus minus lambda 2 square m2 plus k x1 x2 equal to 0.
Shouldn't we input the same lambda to both?
Yeah, did not put the same lambda yet. Lambda 1, sorry. So this is okay? So this gives us what? minus lambda 1 square, and this should be m1 plus k x1 minus k x2 equal to 0. Or what is the equation you're going to get? Minus k x1 equal to minus lambda 1 square m2 plus k, what did I put equal? Here should be plus. Equal to 0. Now what do I need to do? x1 over x2, no?
Mm-hmm.
Yeah? So for the first mode, so for the first eigenvalue, we find, I try to keep symbolic until it gets complicated. Then what are we going to get over there? So you don't need to do both of them. They will give you the same thing. So let's say x1 over x2. What is the notation I use on the class notes for that? Okay, so you see I put here the little number on top.
Mm-hmm.
So let's say we have 1 and 1. So what could be one solution? We're not going to put both of them, I'm just going to put 1. Should be equal to what? K divided by minus lambda 1 square m plus k. Okay, so let's start putting values here because otherwise it's going to get crazy. What was k? 200?
Yes.
200 divided by
200.
what was lambda 1 square?
0.
Oh, 0. So the 0 divided by 200 equal to 1. Okay, so that's very good. So what does that mean?
x1 equals x2.
Yep. So that x1 1 over x2 1 equals 1, or x1 equals x2. Okay, so what does that mean? So when lambda 1 squared equal to 0, x1 equal x2. So what type of motion is that?
Non-vibration, just the two of them moving together.
Correct. So basically, these two objects are moving together, so they're not vibrating, no? With respect to each other. Yeah? So if this one moves one to the right, it's going to move one to the right. When one to the left, it's going to move one to the left. Okay? But here's good. You see, here we found 1. Does that mean that the blocks are going to move 1?
Not necessarily.
No. They just mean that they're going to move the same dimension. We could have found 1, we could have found 25, no? Okay? It only means that block M1 and M2 moves simultaneously okay, which in the fancy word is called rigid body motion. Why do you think they call it rigid body motion?
Because it's all moving as a unit as though it were a rigid body and not moving with respect to itself.
So correct. What would be the definition for rigid body? Object that does not deform under the deformation. So it doesn't change its shape. So here would be the same thing. The distance between the two blocks will move like if it was just one, no? Yeah? So rigid body motion. Okay. So that case wasn't too interesting. But let's find now, we need to do now what? This was for the first one?
Yep. Climb
Okay.
squared.
The second case should tell us what? What will be the vibration of one with respect to the other, no?
Mhm.
So this time, hopefully, we'll find out that they will vibrate in what? Like if one moves to the right, the one is going to move to the
Left.
left. Okay. Hopefully, the math will tell us that. So second one will be for lambdas equal to lambda 2. We go through exactly the same process, so we'll have minus lambda 2 square m plus k minus k minus k minus lambda 2, oh this is m1, lambda 2 square m2 plus k x1 x2 equal to 0. Okay, so by now, slowly you're going to get the procedure. So that means what? Minus lambda 2 square m1 plus k x1 minus k x2 equal to 0. If you want, you can do the second one. So minus k x1 plus minus lambda 2 square m2 plus k x2 equal to 0. Or we can solve for x1, x2, for what? For the second mode. And what would that be? If we just use the first one, will be
It would be k over negative lambda 2 squared m1 plus k.
yeah. So this time, what do we get then? So this would be 200. What was lambda 2?
300.
200. So
One square.
minus. So minus 300 square.
I think when it was already squared, it was 300.
Sorry, squared.
Oh, sorry. So minus 300. And 2 is what? 1 or 2?
2, I think.
I think 1 was 1. Yeah, M2 is 2. Plus K is 200. So this 7 again vector here is going to give us what? So this is 200 divided by,
Negative 400.
so nearly 400, so it would be minus 1/2.
Mm-hmm.
Guys, if you need more time to copy, let me know. Might go a little bit too fast, okay? Sometimes Okay, or what does that mean?
It means they move opposite direction with respect to each other.
Correct,
And
so x1
next to is the greater. No.
equal to minus 1/2 of x2 Okay, so physically, what does that mean? That when the blocks, they say M1 moves 1 to the right, the block M2 is going to move half to the left.
2.
No, it's going to move half, no? Oh, yes, 2 is going to move twice the distance. So x2 equal to x1, yes. All right? But basically now we'll be moving on the opposite direction. So if we want, what we have is what? So summary. Up to now, we have when lambda 1 squared equal to 0. What will be the eigenvector 1? How do we call that on the class notes? I think we call it x1 like this, or no?
Yeah.
Will be equal to what? So this is our first eigenvector. And when lambda 2 squared equal to what? What is it? 200? 300? 300, no? Yeah.
300, yeah.
Second eigenvector will be equal to, so here you have multiple, you can put anything you want. That's 2 So what will you over here when
Would be negative 1 and 2.
you have a, yeah, you can have negative 1. Is that correct? Or is it one half? Hold on 1 second. This is. So if x2 is moving 2, this is moving 1. Yeah. Okay? But you could see this is a good example that you gave me here. So here, how many solutions could we have over here?
Infinite.
Infinite, because we have x equal to x, no? Could give any value to x. What about here?
Also
The
infinite.
same thing, this is infinite. So the reason why I'm pointing that is that to really indicate that this is not the magnitude, no? This is just giving you the behavior, the mode shape, or the direction at which the process is going to happen. But that is not the response. So now, the response should be given by what?
The full solution?
Yeah. Which you remember we had xt equal to so really xt should be equal to a constant times, if you want, 1, 1, e I lambda 1t, which would be 1, plus c2 minus 1, 2 exponential of I lambda 2t. Okay, so we know what? That this is 0, no? Yeah, because lambda 1 is 0. So this is, sorry, this is 1. Oh my goodness. Exponential of 0 is 1.
Mm-hmm.
So the answer at the end would be C1, 1, 1. So the rigid body motion plus C2 minus 1, 2 exponential of I, what was lambda, 300 or 200?
It would be the square root of 300 at this point.
Would be okay. So let's say just lambda 2, okay? Yeah, would be the square root of that. Okay, so we're not going to do it. Oh, what time is it? Maybe we can do it. Okay, I didn't put it here. So now, where C1 and C2 are determined from initial conditions. Okay, so let us assume the following boundary conditions. So x1 initially at t equals 0, we're going to move it a distance of 0.1, okay? With an initial velocity of 0, and then we're going to assume what? That we're going to let everything go, no?
Yeah.
It will be 0, x dot out. 0. What time is it? 15 minutes?
Mm-hmm.
So it's going to take a while. Okay. So now what should we do? Maybe let's start with this one. So what should we do first? We should take the derivative of this one, no?
Mm-hmm.
And see what happens. So we know x of t is equal to C1, 1, 1 plus C2 minus 1, 2 exponential of I lambda t. So what will be x dot?
Be C2 negative 1, 2, I lambda 2, e to the I lambda 2, 2.
All right. So now, what do you need to do? You need to apply these 4 boundary conditions and solve, no?
Mm-hmm.
Okay. So we'll do that next time. It takes a while. I need to check because I never, generally I transform this equation first into the sine, sine, cosine, and I'll solve with that. But we can try to solve with this, okay?
Okay.
We'll solve that tomorrow. But it's not going to be, you see, it's going to be 4 equations for different nodes. So guys, you see that basically the procedure is all the time the same, no?
Yeah.
It's tedious, but. And this part over here is the most difficult, generally, to find those constants. Okay, guys, one last thing. I think I mentioned it before, but really all this concept about eigenvalues corresponding to an eigenvector that correspond to a mode shape, no? So frequency to a mode shape is one of the most important concepts that